So we learned yesterday that Comic Sans is one of the more readable fonts. So I went home and immediately changed my entire slide deck to be in Comic Sans. No, I'm actually just trolling with that. My name is Michael Fairley. I work at Braintree Payments. We make it easy for businesses of any size to accept credit card payments online. We work with thousands of really awesome merchants, including some of these that you probably recognize. So if you're interested in talking about payments, come find me later. I'm going to be talking about immutability today. Immutability, simply put, is when data can't be changed. So in Ruby, this would refer to an object that can't be modified after you create it. But it could also be data in your database that you only ever insert. You never update or delete it. I've had some bad experiences with mutable code in Ruby in the past few years, and some good experiences with some immutable code. So I'm going to give you some examples of pitfalls I've run into and how I've worked around them. The first point is that you already have lots of data in your code that you expect not to change, but that expectation is very implicit. And I think you should make some of this explicit. So as an example, let's say you have a purchase model that a user buys something on your site, and you record who it was, what they bought, and how much they paid. Well, you probably never want any of these attributes to change. Once the user made the purchase, even if you go back and change the price in one of these models, it won't change how much you actually charge their credit card. And if you change the item ID, it won't actually change which item you shipped them. And so this is a fairly common pattern where you have data that's trying to represent events that happened in an external system or in the real world, and you want to make sure those are immutable. So it'd be nice if we had a module like this that we could sort of mix into our active record models and make them immutable. Luckily, that's 5 lines of code. So active record calls the read-only method anytime it tries to save or update a method, and if it returns true, it doesn't actually update it. So here we just say that any record that's already been persisted is read-only, and bam, immutability. And so we can create records fine, but when we try to update them, we'll get an error. And so our code will sort of enforce the behavior we want upon us. And if we're in a script console in production, and we sort of have a momentary lapse where we forget that we aren't supposed to tweak this data, the system will stop you, and that's what you want. And you could even take this one step further and enforce these constraints at the database level. But what if we have a field or some fields that we want to be able to change and some that we don't? So here I've added a status field that's going to progress from processing to shipped to delivered and then maybe refunded later. Well, we want that field to change, but we still don't want the other 3 to. Luckily, there's a gem for that. So we can mark these 3 attributes as immutable, and if we ever try to update them, we'll get an error. And you also run into this problem in your code too, not just in your database. So this is a dubiously helpful method that lets you take a domain name, a path, and some optional query parameters, and it builds the URL for you. And sort of takes care of if there's extra slashes or too few, making sure they work out. So example.com and blog, it just concatenates them together. Or if we pass it a hash, it'll sort of serialize that into the query parameters and tack it on. And so let's say you have this, and you realize that you're using it with the same domain name over and over again. And you extract another helper on top of it. So here we have example.com hard-coded. And our blog URL and our sorted photos look the same. But this hard-coded string is kind of ugly. It's configuration that's been hard-coded into your app, and you want a way to be able to tweak it. So you pull it out into either a constant, or this could be an environment variable, or some data from a YAML file you loaded. And the blog URL looks fine. The sorted photos now has blog in the path, which is a little funny. Let's try that again. That's not quite what we wanted. Something has gone very wrong here. Let's try to figure out what happened. So originally, when the string was hard-coded into the method, every time example URL got called, we generated a new string that was example.com. Once we extracted this constant out, there was only one instance of this string ever being created. And every time we called example URL, we were passing the same string into build URL. and build URL was destructively adding on to the end of it. So the fix for this is pretty simple. You just use += instead of shovel, and that won't modify the base URL. But whoever did the refactoring to extract the string into a constant wasn't paying attention to build URL. They didn't realize that this string was going to be mutated later. It wasn't something that they thought about or should have to think about. So what this person could have done is been a little more defensive and frozen the string ahead of time. And the second the test suite runs, it would have blown up saying you tried to modify this string that you intended to never be modified. And I think this is a pattern that you should be using for configuration and constants and things like that you plan on never ever being modified, just to make sure that when it gets passed around, maybe nine methods down a call stack, someone doesn't realize that the string was supposed to be immutable. And there's one gotcha with freeze, which is that if you freeze an array, it won't freeze the elements inside of it. Or if you freeze an object, it won't freeze that object's instance variables. So there's a gem called ice9 that adds a deep freeze method, which will sort of recursively freeze an entire tree of objects. So when you use YAML load file, you might want to call deep freeze on it and make sure that those configuration variables don't get changed as your application runs. Next up is values. So values conceptually are objects whose identity is based on the data inside of them rather than some sort of external identity. So an active record object is not a value because even if two active record objects have all the same values except for their ID, they won't be considered equal. So values you're probably used to working with are things like numbers and time, where you don't really care if the Ruby interpreter has two different objects that represent the same time. You just care that they're equal. And so there's more values than just the ones Ruby gives you. There's things like addresses and Cartesian points and URIs. And there's a gem that helps you build your own value objects and use them in your system. So it works a lot like structs. Here we've created a new class called point that has attributes x and y. And we can build a point at the origin and get the data out of it that we expect. You can create another point elsewhere, and we get the data we expect. But unlike struct, we can't actually change the data once we've placed it in there. And like I said, the equality is based on the data inside of it and not any sort of identity. So struct works similarly, but with values, you know that once they're equal, they'll always be equal. And you can also add a little bit of behavior to values to maybe make it print a little more prettily, or in this case, to scale the point. But these methods can't modify the value. And so what good are values? Well, skinny controller, fat model has been a mantra in the Rails community for close to 7 years now. And while it's awesome that we've gotten all of this logic out of our controllers, some of our models have gotten a little too fat. Most of you probably have a model called user in your application that has hundreds of methods and thousands of lines of code. And value objects are a great way to decompose these excessively fat models. So let's talk about a hypothetical user model that has, among other things, some shipping address information in it. And the user also has a method to calculate how much it would cost to ship something to that user. So the first thing we do is we make a value that can represent this address. It has the same 4 fields that we saw in the user. And then we can use the active record composed of helper to map the fields from the database onto one of these value objects. So this says that we want to make a method called shipping address that returns an address. And then we give the mapping from the active record database field names to the names that are used within the value object itself. And so when the data gets set on the model as it comes out of the database like this, we can ask for the shipping address, and it'll give us this value object. And we can also assign into it with a value object, and it will decompose it onto the constituent fields. And so there's a little bit of pain with the original version of this user.calculate shipping price, and some of this pain is evident from our tests. We have to require spec helper, which requires our application, which requires all of Rails, and makes our tests take 30 seconds to start. There's hundreds of other tests in this file, which is a pretty clear indication that we're violating the single responsibility principle. And finally, we have to use a tool like Factory Girl, and we have to insert data into the database just to get set up for the test. If instead we moved the calculate shipping price method to address, our test, the only dependency in here is address. There's sort of no need for a factory girl or to talk to the database. And maybe there's a dozen tests in here, but this method or this model isn't excessively bloated. But nicer tests isn't enough reason to make a change like this. It also makes us resilient to sort of changing requirements for the application. What if a user has more than one address? Or we need to be able to ship to businesses as well. With the original code, it's not obvious how we can make these changes. But now that we've sort of decomposed some of the logic onto a value class that can be shared, it's clear what to do. And maybe we want to make it so different items have different shipping prices. Here we move the calculate shipping price method onto item and have it take an address. But if this was taking a user instead, it wouldn't be clear how to make these changes. So there's a pattern here, which is that having different pieces of your system communicate with value objects gives you a lot more flexibility. And there's another win from this example. So let's say you add a checkbox to your website that says, use my billing address as my shipping address. Well, at some point, you would need code that looks like this. And if you ever added a new field to the address, like country, for example, you wouldn't remember to come update this. But if you're using these value objects, then you can just assign one to the other, and it's resilient to change in the future. So next up is event sourcing. Event sourcing is when you capture all of the changes to your application state as a sequence of immutable events. And this is best explained with an example. We're going to use a bank checking account. So you open the account, you put $1,000 into it, and your balance is $1,000. You buy a conference ticket, your balance goes down. You get paid, your balance goes up. You buy a book, and you return it, and your balance goes back to what it was before. So to break this down a little bit, the events in this system are the debits and credit against your account, the 5 transactions we saw. And the derived state is the balance. You'll notice that if I take away the balance, each of you could recompute it based on the events you see up top. So the balance here is sort of the state you care about. When you open your bank account, you really want to look and see how much money do I have that's safe to spend. But the transactions you've made are actually the events that have led to that state. And because we have this log of events, we can ask some interesting questions and do some interesting things with our data. We can say, what was account 110's balance 7 days ago? And if we look at the events leading up until that point in time, we can answer the question pretty easily. And then events are immutable. And so to revert them, rather than, so for the returning book example, instead of deleting the fact that we bought the book at all, we inserted a new event that was the opposite and returned the money to the account. And finally, events can be replayed in a different time or a different place. So if there was an error in production at this bank, they could pull down the event log that was happening when the error occurred and replay that event log locally up until the point in time where the error happened. And the developers would be looking at the system in the exact state where the error occurred. Or if they're ready to roll out a new version, you can play an event log against the old version of the code and the new version of the code and make sure that they agree at every step along the way. And there's another event source system that most of you use almost every day, and that's Git. So in Git, the events are commits. The derived state from these commits is your working directory. You can reconstruct past state and ask questions like, what did my working directory look like as of commit A321BD? And similarly, when you revert an event in Git, instead of undoing the event, it adds a new event that's the opposite. And then Git rebase is a form of event replay where you take some events from one branch and play them on another. A few years ago, I was working at a family history startup, and we built a family tree feature, and we decided to event source all of the changes to this family tree. So anytime someone came and added a family member or changed a relationship, we logged the event. And I'm going to tell you some of the awesome wins we got from this and why we made the decision in the first place. So you can think of family trees as a graph where people are the nodes and relationships are the edges. And up until this point in time, we had been using Postgres to store all of our data. And Postgres is rock solid. It had never lost our data. We knew how to run it. But relational databases aren't great for storing graphs. Your queries get ugly. They're a little slow. And sometimes you even need to make multiple round trips to the database to fully execute the query. On the other hand, there are these new fancy pants, hipster, NoSQL graph databases that make querying graph structure. Sorry, the Wi-Fi popped up. Perfect. So these graph databases are super efficient at querying graph structures and traversing along them, which is exactly what we wanted for our family tree. But we didn't know how to operate this database, and we didn't really trust it to keep our data in a durable fashion. So we decided to record the event log in Postgres and store the computed state of the graph in the graph database. And so we knew that if the graph database fell over in the middle of the night, we have a canonical copy of all of our data in Postgres where we trust it. Another cool thing we got from this was an audit log. So every so often, we would have some malicious users come and damage a family tree either by adding fake information or removing the information that was already there. And it seems like it would be a pain to clean up, but all we had to do was find each of the events that one of these malicious users caused and revert them. And then finally, we decided that the family tree wasn't important to the business and that running this graph database was a bigger burden than the benefits that it was giving us. So we decided to move everything back into Postgres. But if you've ever done this before, you know that copying data from one database into another is kind of painful, even more so if they have very different data models like a graph database and a relational store do. So instead of having to copy the data out of the graph database back into Postgres, we changed our application code so that it knew how to write events into Postgres, and then we replayed the entire event log, and at that point in time, Postgres and the graph database had the exact same computed values, and we just turned the graph database off, and that was the end of the story. So you might run into problems where event sourcing is an awesome solution that gets you some cool wins like this. You can also do clever things like store your computed state in memory, where it's very fast to query, or in Redis, where it's very fast to query, but still have a durable record of everything that got you there. There's a bunch of rules in software engineering and computer science that immutability helps let you sidestep a little bit. So there's a famous quote: there are only two hard problems in computer science, cache invalidation and naming things. Well, if all the data you have cached you know will never change, then cache invalidation is no longer a problem for you. You've probably seen this with the Rails asset pipeline. So for every version of each of your assets, Rails appends a version hash onto it, and it knows that every single request against that URL will always return the same data. So it tells the browser and proxies to cache it for up to a year, which is effectively forever. And database normalization is also interesting. If you go to Wikipedia and figure out why database normalization exists, it has this to say: the objective is to isolate data so that additions, deletions, and modifications of a field can be made in just one table. Well, if you're never updating or modifying this data that's copied across multiple tables, you don't actually need to normalize if you have reason to leave your data denormalized. And then finally, immutable objects are automatically thread safe. Value objects and persistent data structures can be shared across threads without having to worry about any sort of locking. As with everything, there are trade-offs when you choose to use immutability. So I'm going to point out some of the downsides. A big one is performance. When you're using immutable data structures and immutable objects, you end up allocating and copying a lot more data, which is going to be slower and consume more memory. You also sacrifice some flexibility for immutability. Immutability is a constraint that you're placing upon yourself. And maybe your domain or your performance requirements or libraries you're using don't work well with immutability. And in that case, it's not for you. Ruby is also not a help towards immutability. We can reassign constants. We can reach into other objects and change their instance variables. There's even a gem that lets you unfreeze a frozen object. So the powerful flexibility that's built into Ruby sometimes makes putting constraints on ourselves a little more difficult. And then finally, deletion is also a form of mutation. So if you think about Twitter, conceptually, tweets are immutable. Once you write one, you can never go back and edit it. So it seems like Twitter should be able to cache it for forever. But you can delete your tweet, and Twitter still has to worry about all the complicated things that come with cache invalidation there. If any of this interested you, I have pointers to a handful of next steps. And this URL in the bottom corner will have links to everything I'm about to mention, and it'll be up for the rest of the presentation. I'd recommend learning one of these 3 programming languages. They each have immutability baked into the core, and at times will make changing things downright hard. You might not find them useful for your day-to-day work, but learning them will help you learn more about immutability and make you a better Rubyist. Rich Hickey is the creator of Clojure, and he's given a handful of really awesome talks in the past few years about immutability. I talked for 5 minutes about values, but he has a 90-minute talk about values that's incredible. There's 2 awesome texts about value objects. One of them is Domain-Driven Design, which is a book that talks a lot about how to have value objects and mutable entity objects interacting together in an application. And then the C2 wiki also has some great articles about value objects and why you want them to be immutable and what to do if you can't make them immutable. Gary Bernhardt has been talking about this idea of the functional core imperative shell, where all of your domain logic lives in pure functional, entirely immutable parts of code that are then tied together by this larger, mutable imperative shell. And he gave this talk at RubyConf this past November called Boundaries, where he explores this idea in great depth and gives some cool examples. And then finally, Martin Fowler has the canonical text on event sourcing. Talks about a bunch of examples, different use cases, why you would want to do it, and some pitfalls you'll encounter along the way. And that's all I have for you, so thank you. How much time do we have?
2 questions. Take some questions.
Okay, I also have a bonus round if we have like 5 minutes.
Yeah, 5, we got 5.
Awesome. So I mentioned persistent data structures earlier. So persistent data structures are immutable data structures where when you try to change the data inside of it, rather than changing it, it actually returns you a new copy with the modifications applied to it. And so there's an awesome library for doing this in Ruby called Hamster, and I believe these are also built into Rubinius. So as an example, we have a vector called foo that contains the numbers 1, 2, and 3. When we add a 4th element to it, we're assigning this into bar. And so bar contains the modification we just made, but foo remains unchanged. And when we try to change one of the elements in the vector, Baz has the change, but foo doesn't. And so to help explain why this is useful, we have the 3 Stooges. So the 3 Stooges were in a movie called Soup to Nuts. And at this point in time, the 3 Stooges were Moe, Shemp, and Larry. In the next movie, Meet the Baron, Shemp left the Stooges, and Curly joined on as the 3rd Stooge. And then in another later movie, Gold Raiders, Curly left and Shemp came back. Here, if we were sharing the same array or set between these 3 movies of the cast and we changed it, when we, for the second movie, took Shemp out and added Curly, it would have changed the cast of the first movie, and we would have gotten some unexpected results. But with these persistent data structures, the cast for each of them is exactly what we expect. And so you're asking, so hamsters just call and dupe a bunch, right? No, there's actually some very awesome computer science going on here. So we have this vector of the numbers 1 through 7, and you'll notice that the leaf nodes of this tree here are the numbers 1 through 7 when traversed in order. And you'll notice that old is sort of a pointer to the root of the tree. So when we add the number 8 to the vector, we end up with a new tree. And if you look at new and do the in-order traversal of the leaf nodes, you again get the numbers 1 through 8, as you expect. But old and new are sharing almost all of the nodes. So it's much more efficient and faster and takes less space to share these nodes like this than to do a complete copy. And now I'm actually done.